So to start off our discussion of some of the technical aspects of this method, I want to dig a little deeper into the pseudocode and think about some of the decisions that I made here. The first thing you need to consider when you're implementing any kind of algorithm like this is making sure that you've given the computer a way to know when to stop, right? But down here in the bottom left, I actually have several different options for doing this. One, and this is kind of the most general purpose one, I think, is just to set a maximum number of iterations, right? Set a maximum number of times you can go through the loop. And you see, I actually have that up here in my pseudocode for the bisection method. The Another way is to look at the absolute difference in the terms. Because one thing I want to point out here, we're generating a sequence of numbers with this algorithm, right? You've got the first midpoint, then you've got the midpoint of the second smaller interval, then the midpoint of the third even smaller interval, and so on. So we've got a sequence here. And one way to tell if we've gotten to where we want to be is to look at two successive terms of the sequence and say, well, has this difference dropped below a certain level? That works sometimes, and you'll see code that uses this. There are some kind of weird considerations with this one, though. There are sequences where the sequence that you get by looking at the difference between successive terms converges to 0, but the actual original sequence itself diverges. Right? So yeah, this one is okay, but you got to be a little careful with it. Another approach is to use this relative difference. Right? That one it is safer. Right? That's a safer choice. And finally, down here we have looking at some specific value, something that may be specific to your algorithm. In our case, for example, we know that the function values are supposed to be going to 0 because this is supposed to be approaching a root of the function. So, okay, in our case, we could also look at the function values of the terms in our sequence. Say, okay, are these going down to 0? Or have these dropped below a certain level? All right, over here, if you look at the code, I've actually implemented something a little different here. Right, this piece here says stop if b minus a divided by 2 has dropped below some predefined tolerance, some small value, 10 to the negative fourth, negative fifth, whatever works for your process. How is that going to be a stop condition? Well, look at what I've done. I have my current interval from A to B, and I've redefined P. Right? I have my new value for the midpoint. All right, B minus A is the length of the interval. B minus A divided by 2 is half the length of the interval. So that's this size here and this size over here. Well, the way the method was designed, I know that the actual root is on that interval somewhere, right? Say, I don't know, say it's right here, right? So what do I know about it? Well, at this point, because of the current size of my interval, I know that actual value is no further away from my midpoint than this distance here, and that distance is b minus a divided by 2. So that works, but it is kind of unique to our particular algorithm. Okay, the other thing I want to highlight is this part right here where I calculated p. I'm looking for p is the midpoint of the interval from a to b, right? So I mean, you could reasonably look at this and say, well, look, why did you do this messy thing? Why didn't you just do p is equal to a plus b divided by 2? Well, that's the midpoint, right? From all the way back in your analytic geometry classes, pre-calculus classes. Well, there's a really technical reason that I didn't do it that way, and it goes back to our idea of machine precision, right, and rounding error. It's possible that if you're looking for a really high level of accuracy, you've got a really small interval here. it's possible that if A and B are both rounded up, that A plus B divided by 2 is actually pushed outside the interval. You actually get a result that's greater than B because of the rounding, right? So I avoid that by doing this otherwise kind of weird looking construction, right? This B minus A this B minus A, worst case scenario, that becomes 0 when it shouldn't be. A plus 0 is A, and you kind of get stuck on that endpoint until you finally hit this ending condition. At which point you've gotten down to a fairly small interval at this point anyway, so A should still be a reasonably good approximation. So I want to do two things on this slide, both under the banner of correctness. What correctness means, it's a computer science term that refers to proving that the algorithm does what you say it does, right? Proving that in our case, if we go through this process enough times, we're going to end up with something that is an approximate value of a root of this function. So the second thing we're going to do is in this inequality down here, we're going to get an idea of what the maximum error is, and kind of by extension, how quickly we can expect this algorithm to converge. So we'll walk through this here. We start off if f is continuous on the closed interval from a to b, that's what that c part means, and f of a times f of b is less than 0. That's just saying f of a and f of b have different signs. So we've really just kind of done the setup part for the intermediate value theorem here. Then the bisection method generates a sequence, p sub n, those are the midpoints, that converges to the actual root of p, to the actual root p of f with this inequality here. All right, so let's take a look at this. The left-hand side, remember p sub n is the nth midpoint, and p is the actual root. So this part here, this is our error. It's how far our approximation is from the actual exact answer. And this inequality is saying that that has to be less than or equal to this expression here. If you look closely at that, right, it's always good to look at these error bounds and think about what the dependencies are. So the maximum error is dependent first on the size of the interval, that's b minus a. So it's clearly going to be to our advantage to make that interval as small as possible. And it depends on the number of iterations. And obviously, as n gets big, 2 to the n gets even bigger. We're dividing by a big number. We can expect that to go to 0. Okay, so how can we actually prove this? So the proof of this is pretty straightforward. What I want to do first is look at the lengths of each of these successive intervals. Right? So when n is equal to 1, the length of our interval is just b minus a. When n is equal to 2, it's b minus a divided by 2, right? Every time it's going to shrink by a half. So when n is equal to 3, it's b minus a over 2 squared. Hopefully at this point already it's enough for you to see the pattern. If we continue this down here, the nth interval is going to be b minus a over 2 to the n minus 1. Okay, now let's look at this expression. The absolute value of Pn minus P. Okay, that's the distance between the midpoint of our interval, P sub n, and the actual root. Okay, so our interval looks like this at this point. And our midpoint is here. And the actual root, I don't know, it's in here somewhere. Okay, the maximum distance between the midpoint and the actual value is going to be half the length of this interval, right? It has to either be in here, and that's b minus a over 2, or it has to be in here, and that's also a distance no more than b minus a over 2. Okay, so this is less than or equal to b sub n minus a sub n. Those are the endpoints of the nth interval times 1/2. Well, what do I know about the length of this interval? I know that it's equal to this, right? So this is equal to b minus a over 2 to the n minus 1 times 1/2, which is b minus a over 2 to the n. And that's what I wanted to show. Right, so right there, I've established that this inequality is true. What does that say about convergence? Well, if you go back to your second semester calculus class, where you spent an awful lot of time talking about sequences and convergence, and you may have more than once asked yourself, what does this have to do with anything? Well, this is where it has to do with something. All right, as n goes to infinity, excuse me, that should be an inequality at that point. As n goes to infinity, this side goes to 0, which means that the sequence defined by p sub n is converging, and that's what we needed to show. So there are a couple of interesting implications of what we just did. The first one, and I know I've hinted at this before, this method always works. If the initial requirements are met, you've got a continuous function, and the signs of the endpoints are different, you can be absolutely certain that you will eventually get an approximation to within whatever your level of tolerance is. It will always work. The downside is that in general it works slowly, right? And to see why, take a look at this. Take a look at this upper bound on the error here. All right. Looking at that, I mean, you could reasonably look and say there's an exponential function down in the denominator. Those grow really fast. So why is this not converging really quickly? Well, yes, exponential functions grow quickly, but the exponent base 2, not all that fast, right? And to see why, take a look at this example. Assume, let's say that b minus a is equal to 1. It's actually fairly common. It's easy to write a quick program that will calculate f of 0, f of 1, f of 2, f of 3. You're looking for 2 where the signs change, right? And let's say you do this 10 times. I mean, that's a fair number of trips through the loop, right? What do we know about our maximum error at this point? How far off could we potentially be? Well, b minus a over 2 to the n is going to be 1 over 2 to the 10th. That's 1 over 1024, which is just a little fraction less than just 10 to the negative third. You've gone 10 passes through this thing, and you've only managed to get yourself out to 3 decimal points worth of accuracy. Really not that good. And as you'll see, even just going through the rest of this chapter here, there are algorithms that will do better than this. All right, now that we've developed the algorithm, we've talked about some of the pros and cons of the algorithm, we've proven that the algorithm does what we say it's going to do, and we have an error, a bound on our maximum error. The next lecture, we're going to actually do an example and see how you can implement this thing.